Module 3, Lesson 5, Finite Automata and Language Modeling Computation. For this module, we'll be covering the definition of finite state automata, the characteristics of your finite state machine, a state diagram and a state table, the modeling computation, your phase-structured grammar, and language generation. What is a finite state machine? Many kinds of machines, including computers, can be modeled using a structure called finite state machine. By definition, a finite state machine or finite state automata is simply a state machine that is a mathematical abstraction, sometimes used to design digital logic or computer program. It is a behavior model composed of finite number of states, transition between those states, and actions, similar to a flow graph, in which one can actually inspect the way logic runs when certain conditions are met. The characteristics of your finite state machine. A finite state machine consists of a finite set of states, a designated start state, an input alphabet, and a transition function that assigns the next state to every state pair. It has a finite internal memory and an input feature that reads the symbols in a sequence without one at a time without going backwards, and an output feature which may come in the form of a user interface once the model is actually implemented. Some types of finite state machines eventually produce an output, while others simply do not produce an output. Some states are designated as accepting states. A finite state machine operation begins from one of the states, which is called a start state, and then goes through transitions depending on the input onto your different states, and can end at any of those available states. However, a certain set of states that are successful flow of operations eventually are simply marked as accept states. Finite state machines are actually used in many diverse applications, which includes spell checking programs, grammar checking, indexing, searching large bodies of text, speech recognition, HML, HTML, and network protocols. Finite state machines can solve large number of problems, among them electronic design automation, communication protocol design, parsing, other engineering applications. In biology, artificial intelligence research, state machines or hierarchical state machines are sometimes used to describe neurological systems and also applied in linguistics. In computer science, finite state machines are widely used in modeling application behavior, design of digital hardware systems, software engineering compilers, network protocols, and the study of computation and languages. This is an example of your finite state machine of a particular automated door. As mentioned, your finite state machine simply looks like a flow graph, where it contains a corresponding vertex or node containing your states and edges that are directed and are considered to be transition edges. Along these considered transition edges, you also have conditions that are eventually given in order to cause transition from one state to the next state. By definition, a current state mentioned in your finite state diagram is a state determined by the past states of the system. As such, it can be said to record information about your past. It reflects the input changes from the system start to the present moment. The number of names of states typically depend on the different possible memory states of your given computer, which are often described in a power of 2. A transition indicates a state change and is described by a condition that is needed to be fulfilled in order to enable transition to go from one state to the next state. While some corresponding finite state machines are often associated with an action. Basically, an action is a description of an activity that is performed at this given moment when you enter your corresponding state. As such, on the given example on your automated door, you have the different actions: entry action, which is performed when entering the state, and an exit action, which is performed when exiting your corresponding state. an input action is performed depending on the present state and the input conditions, while a transition action is performed when performing a certain transition condition. A finite state machine can actually be represented either as a state transition diagram seen on the previous slide or as a state table. When described as a state table, this diagram would now appear like this. So on a particular table, you have a present state, and then you have inputs which are given to be in the columns of 1 and 0. And the values inside your respective cells are your respective next states. So seen on this particular diagram, these are your present states, while these corresponding states are your next states depending on your input, which is either a 0 or a 1, since this particular finite state machine implement a digital circuit. All the possible inputs to the machine are enumerated across the columns of the table, and all possible states are enumerated across the rows. So it's actually easy to see if the machine is in state 1 and the input character is 1. The machine will stay in state 1 until the next character, which is a 0, arrives. If a 0 arrives, then the machine will go to in transition from S1 to S2, as seen on your corresponding second column. In the diagram, it is also denoted by the arrow from S1 to S2, labeled with a corresponding transition condition input of 0. Your corresponding state table may also appear like a one-dimensional state table, which is also called a characteristic table. A one-dimensional state table actually looks more like a truth table, whereby it actually shows the inputs that are placed on one side, which is normally on the left-hand column, separated from your outputs, which is seen on the right-hand column, which typically represents the next state of the machine or its output. Hence, this is a one-dimensional state table. Note A, B are your corresponding inputs, while your current state is given to be S1, and your outputs would be the next state, and in some cases, some finite state machines also output a corresponding value. Therefore, in this particular finite state table, you have a corresponding output column. You could actually convert your corresponding state table into a diagram or vice versa. When converting your table into a diagram, it is possible to draw them using this corresponding sequence. Simply observe on the table how many states are given on your respective table. Then draw circles to represent the states that are given on your table. For each state, scan across the corresponding row and draw an arrow to the destination state. There can be multiple arrows for input character if you are creating an automaton that is a non-deterministic finite automaton. Designate your corresponding start state, and the start state is usually given a formal definition on your automaton. Designate one or more states as your accept states, which eventually shows when the sequence of your inputs eventually end. This is one example of your finite state machine. This particular model of your sequential circuit allows us to determine how this particular circuit behaves. And as seen here, you have what you call a corresponding delay circuit, which is often referred to as a D flip-flop. As the name implies, the output of this particular circuit is eventually delayed depending on the clock pulse that is given on the system. This only replies on a given particular clock pulse and will only output values that are stored inside your D flip-flop. Hence, if you evaluate this behavior using a corresponding logic state table using logic values of inputs of ones and zeros, then you'd end up with this corresponding state table. And as mentioned, this particular table can be converted into a diagram, and when converted into a diagram, it then appears like this. And if you do try to observe your corresponding state table, you would see that your corresponding state table actually resembles that of a truth table. Now, there are also different ways to illustrate your corresponding state diagram. One is called the Mealy model, whereby the output depends on the present state and input, and the other one is the Moore model, whereby the output only depends on your corresponding present state. This now is a Moore model corresponding state diagram, whereas this one is referred to as a Mealy model state diagram. Let's try to evaluate then a behavior of this corresponding finite state machine called an SR flip-flop. An SR flip-flop is often designated like this, as a box, whereby you don't technically know what is inside your corresponding box. And basically, it's not important as long as you know how this particular circuit behaves. However, if you do want to know what's inside your corresponding box, it's simply a cross-coupled NOR or a cross-coupled NAND, illustrated like this. And if we evaluate then how this particular flip-flop behaves, we then create the state transition table for your respective flip-flop. That means if your S is 0 and your R is 0, your corresponding next state would simply be your respective previous state. So if the previous state is 0, it remains 0. If the previous state is 1, it remains 1. However, if your S has an input of 0 and your R an input of 1, this is often referred to as your corresponding reset state, whereby your next state will always be 0. And if your S value input now is 1 and your R value is 0, this is often referred to as your set state. Therefore, your corresponding flip-flop simply inputs a value of 1 and stores the value of 1. However, if your S is 1 and your R is 1, therefore, this corresponding condition is not applied to your respective flip-flop, hence often referred to as a running condition, because as defined on your set reset flip-flop, you cannot set and reset at the same time. Let's examine the behavior of this corresponding JK flip-flop. This is the state table of your given JK flip-flop. And if you notice, it's very similar to the behavior of your SR flip-flop. This is due to the fact that your JK flip-flop is simply created from your SR flip-flop. However, if J is 1 and K is 1, it eventually operates like a toggle switch. Whatever is the previous value, he then toggles it and outputs the opposite value. So if the previous value is 1 and the inputs now are both 1 for J and 1 for K, the output becomes 0. Whereas if the present state or the previous state is 0 and you input J1 and K1, then it toggles the value again from the previous value of 0 to a new value of 1. Modeling computation. Words in English language can be combined in various ways. The grammar in English tells us whether the combination of words basically is a valid sentence. The process is basically similar. However, this particular process involving model computation is more concerned regarding syntax on how you form your respective sentence rather than its semantics or meaning. Meaning, the syntax of a natural language that is both written or spoken English in different languages like English, French, German, and Spanish is extremely complicated due to the different meanings and semantics used by the different words on these different languages. When you do model computation, as long as you follow a correct syntax on how to form your given sentence, then that corresponding concept is simply correct. Research in automatic translation of languages eventually led to what you call this formal language. However, unlike your natural language, there is a specified, well-defined set of rules of syntax that this technique eventually follows. The rules of syntax are not only important in linguistics, but it's also important in corresponding programming languages, which is why when you create a program and you place a wrong sequence of operations or wrong character on your given program, it evolves into a syntax error. Since your corresponding modeling computation similarly follows the rules of your corresponding English language, here are some of the corresponding rules of grammar in an English language. So you have a sentence that's made up of a noun phrase followed by a verb phrase, or a noun phrase that is made up of an article followed by an adjective followed by a noun, or a noun phrase made up of an article followed by a noun, or a verb phrase that is made up of a verb, or a verb phrase that is made up of a verb followed by an adverb. And it is often customary to use these rules in order to form valid sentences that are acceptable by making series of replacements until no more rules can actually be used. On a given phase-structured grammar applied for modeling computation, the primary concern, as mentioned under the given phase-structured grammar, is syntax. On a given phase-structured grammar, you have what you call a vocabulary. A vocabulary basically is a set of alphabet or characters, which is finite and non-empty, which implies that there are always symbols that are often used for your vocabulary when you create what you call a phase-structured grammar. A word or a sentence over your vocabulary basically is formed by creating a string of finite lengths of elements of your corresponding set V, or sets of symbols. So all we have to do is to create a string of symbols. Therefore, we create what you call a word. The empty string or null string is actually denoted by lambda, is basically a string which contains no symbols. And the set of all language over your vocabulary is also known as the subset of your corresponding set V. The elements of your vocabulary that cannot be replaced by other symbols are eventually referred to as terminals. Those that can be replaced by other symbols are referred to as non-terminals. The rules that specify when we can replace a string on your corresponding vocabulary with another string is called production of your grammar. We often denote them with an arrow pointing to the right. The production eventually specifies what particular character can be replaced by what character within your given string. So on a given phase-structured grammar, it basically comprises of a set of vocabulary, a set of starting characters, a set of terminating characters, and a corresponding production process. Your respective production process contains at least one non-terminal character on its left side, which is usually taken from your set of vocabulary. This is one such example. Let's say your corresponding grammar G contains the respective vocabulary containing the following characters: lowercase a, lowercase b, uppercase a, uppercase b, uppercase s. Then you have terminating characters, which eventually denotes small letter a and small letter b. The S on your vocabulary simply means that this is the start symbol. So from your corresponding production P, it means that when you have S, it involves that and points to a particular starting character that your sequence can begin. It also shows us what particular character is then replaceable by a different character. So on a given phase-structured grammar, you eventually apply concatenation on your strings in order to produce different corresponding strings from your given production. The sequence of steps used to obtain your output string from your given startup character string is then referred to as derivation. Let's try to derive then the following language of grammar that can be formed from your given vocabulary containing characters smaller or lowercase a, an uppercase a lowercase b, an uppercase b, and an uppercase s, with a terminating condition, lowercase a, lowercase b, and s denoted to be your starting symbol, pointing to a particular production equal to this. Therefore, you'd end up with a, uppercase a, lowercase b, and a. That is directly derivable from uppercase a, uppercase b, and lowercase a, because you could actually replace uppercase b with lowercase a and lowercase b. Okay, therefore you'd end up with a derivable string which is equivalent to a, b, a, b, a, b, a from your corresponding startup string, that is uppercase a, uppercase b, lowercase a, because a can be replaced with respectively b, uppercase b, and uppercase b. And we denote that uppercase b can be replaced with a, lowercase b. Okay. So in both the last two steps of your corresponding derivation, you could actually create the remaining two respective language of your grammar. So hence, when we perform language generation, remember, you are more particular with regards to syntax rather than semantics, which means that the strings that you eventually can create from your given language may actually mean gibberish. So given here is the respective notation for the language of your grammar. So if the language of your corresponding grammar contains the following vocabulary which we have applied, and your terminating condition, lowercase b, then when we produce characters from your given production, you'd end up only with two possible strings. That is BA, and the other string is A, BA, BA, BA. If you then apply creation of the language of grammar from your corresponding vocabulary containing uppercase S, uppercase A, lowercase b, and a terminating character of lowercase b, with uppercase S denoting your starting character on your given production process. Therefore, it's possible to have only two particular strings that can be formed from your language of grammar. So we derive then from the starting character lowercase a, uppercase a, and then we replace uppercase a with two lowercase a's, thus forming AAA. Then on the next corresponding process, you could start off with lowercase b. However, after starting with lowercase b, there are no other strings of characters that are eventually attached based from our production. Therefore, the next string would only contain b. Hence, you can only produce two strings of this corresponding production process. On this given example this time, your vocabulary set contains an uppercase S, 0, and 1, and your terminating characters would either be 0 or 1. Note that S, uppercase S, denotes the start symbol, and if S points to 1, while on your production S also points to 0, therefore, it's possible to have the following bit strings. So it's possible to have a bit string containing 0 only, because 0 likewise is a terminating character. Okay. However, if your string starts with 1, followed by S, and you replace S with 0, then you have 1, 0. If your string starts with 1, and it follows that S is also 1, therefore you'd end up with 1, 1, and then if you replace S there with 0, therefore you terminate the process and end with 1, 0. Hence, the different language of grammar that can be converted or produced from this given particular production process becomes infinite. This ends the corresponding Module 3, Lesson 5.